Hey everyone, and welcome. Today, we're going to learn a new language, but it's not Spanish or Mandarin. It's the language the universe itself is written in, mathematics. We're going to take a journey together, all the way from the elegant clockwork grammar of Isaac Newton to the seriously mind-bending poetry of Albert Einstein. And by doing that, we're going to unpack the story of space, time, and gravity itself. So, if we want to really get what Einstein did, we first have to understand the language that absolutely ruled physics for hundreds of years. This was the language that described a universe that was predictable, certain, and ran like a perfect machine.
You see, for guys like Sir Isaac Newton, the cosmos was this incredible, massive clock. Once it was wound up, it just ticked along, perfectly and predictably. And the rule book for how every single gear and spring in this clock worked, well, that was written in the language of algebra, geometry, and the hot new thing back then, calculus. And it all started pretty simply. I mean, Galileo looked at a cannonball flying through the air and had a brilliant idea. He realized you could just split its motion into two parts. You've got the horizontal motion, which is basically constant, and you've got the vertical motion, which is just a simple story of acceleration. With a little bit of algebra and geometry, you could map out its path perfectly. But then Newton came along and had this amazing leap of imagination. He thought, okay, what if we put a cannon on a crazy high mountain and fired a cannonball so fast that as it fell, the Earth literally curved away from it at the exact same rate. It would never land. It would be in orbit. And that was the aha moment. He realized the same math that describes an apple falling from a tree is what describes the moon orbiting the Earth. And that massive insight led to this, the core rule for the entire clockwork universe. Just one equation, Newton's law of universal gravitation. It was like a single mathematical sentence that connected everything to everything else, from a tiny pebble to a giant planet. It was simple, it was elegant, and honestly, it seems like the final word on the matter.
Now, this is absolutely crucial to understand. The whole Newtonian system, the whole clockwork universe, was built on top of two ideas they thought were unshakable. First, that space was this fixed, rigid stage where everything happened. And second, that time was a universal clock, ticking away at the exact same rate for everybody, everywhere in the universe. I mean, that wasn't a crazy assumption, right? It just felt like common sense.
But that common sense, that beautiful, perfect clockwork universe, was about to run headfirst into a single, stubborn fact. A fact that just refused to play by the rules. Yep, the cosmic speed limit. But here's where it gets really, really weird. It's not just fast, it's constant for everyone. So if you're standing still, light zips past you at this speed. But if you get in a spaceship and chase after that beam of light at, say, half the speed of light, it still zips past you at the exact same speed. In Newton's world, that's just impossible. It's a complete paradox, and it meant the old language was broken. So to fix this paradox, Einstein didn't just tweak the rules. He took the whole rulebook and threw it out. He completely tore down the old foundation. Gravity? It wasn't a force anymore. Now it was all about geometry. And the most shocking part? That absolute unchanging space and that universal ticking clock of time? Gone. Demolished, replaced by one single interwoven thing. To even begin to describe this new reality, a whole new mathematical vocabulary was needed. Einstein's first big step was special relativity, and it basically created the new grammar for a universe where the speed of light was king, even if that meant throwing our old ideas about space and time right out the window.
Okay, don't let the equations on this slide scare you. You don't have to solve them to see the revolution happening. These are the Lorentz transformations. Just look closely. See how the equation for the new time coordinate, that's t prime, actually depends on the old space coordinate, x? And the new space coordinate, x prime, depends on the old time coordinate, t? They're all mixed up. Space and time aren't separate things anymore. The math literally tangles them together.
And that's what gives us our new stage for reality, space-time. You have to think of it like a single four-dimensional fabric. Every single event that has ever happened, or will ever happen, from you sipping your coffee right now to a star exploding billions of light years away, has a unique address in this fabric, with 3 coordinates for space and 1 for time. Now, special relativity was a huge deal, a massive breakthrough. But it had one giant glaring hole in it. It described a flat spacetime, a universe where things moved at a constant speed in straight lines. It had no room for acceleration, which meant it had no room for gravity. The language was still missing a key part of the story.
And that leads us to Einstein's masterpiece, the main event, general relativity. This is where the language of physics completely transforms into the language of pure geometry, and our most familiar force just vanishes.
So this is the big question, right? If the Earth isn't pulling on you with some invisible rope, then why are you stuck to your chair right now? Why do planets bother orbiting the sun? What's going on?
And the answer is just so profound and beautiful. It turns out that mass and energy don't create a force at all. What they do is they warp and bend the very fabric of space-time around them. Think of putting a bowling ball on a trampoline. Everything, you, me, the Earth, even beams of light, is just trying to travel in the straightest possible line through this now curved landscape. What we feel as the force of gravity is just the experience of moving along the straightest possible path on a curved surface.
So, okay, great, but this creates a massive mathematical problem. All the old math that worked on a flat grid is totally useless now. You need a completely new kind of mathematical tool, one that works on any surface, no matter how it's bent or stretched. You need a language that doesn't care about your point of view. And that tool has a name, the tensor. You can think of tensors as the native language of curved spacetime. They're these amazing mathematical objects that can package up all sorts of complex physical information, like energy or momentum or the actual curvature of spacetime itself, in a way that stays true no matter how you're looking at it. Now, this matrix might look a little intimidating, but just think of it like a really sophisticated file folder. This specific one, the energy momentum tensor, is the folder that holds all the information about the stuff, the matter and energy, at one single point in spacetime. It's one of the most important nouns in our new cosmic language. So now that we have our new vocabulary, these powerful tensors, we can finally write the master sentence of general relativity. One single, incredibly concise equation that describes the entire dance between spacetime and everything inside of it. And here it is, the Einstein field equation. I know it looks complex, but it's better to think of it as a sentence, a cause and effect statement, written in the language of tensors. On one side, you have the math that describes geometry, and on the other, you have the math that describes the stuff. In the end, this whole monster of an equation can be translated into one simple, jaw-droppingly profound sentence. The stuff on the left side is just a very precise way to describe the geometry, the curvature of spacetime. The stuff on the right side is that tensor we saw, the one that describes all the matter and energy. And the equal sign just means is determined by. So put it all together, the geometry of spacetime is determined by the matter and energy within it. It's just that elegant.
And believe me, this isn't just some abstract idea. This new language makes real-world predictions. It solved a mystery about Mercury's orbit that Newton's laws never could. It predicted black holes and the expansion of the universe before we had any idea they were real. And, get this, every single day, the GPS on your phone has to use this math. It corrects for the fact that time literally takes faster for the satellites up in orbit than it does for us down here, just so it can tell you where to turn next.
So, we've gone on this incredible journey, from the simple algebra of cannonballs to the wild world of tensors and curved spacetime. Each big leap forward in understanding the universe required us to invent a new, more powerful mathematical language. Which really makes you wonder, right? As our knowledge keeps growing and we bump into new mysteries like dark matter and quantum gravity, what new kind of language, what new kind of math are we going to have to invent to finally read the next chapter of the universe's story?